Hello, multivariable calculus students. Ms. Deer back on the mic. We have been talking about creating Taylor polynomials. These are polynomials that behave like a non-polynomial function around a center. So remember, if our center is C, then we want the value of the polynomial to be the same as the value of the function at C. So our polynomial starts with f of C. Then we also want the value of the derivative of our polynomial to be the value of our function, the derivative of our function. So we have plus f prime of C times x minus c to the 1. Then we want our second derivative of our polynomial to be the value of the second derivative of our function. So we have the second derivative of c, x minus c, that's a c squared over 2 factorial. And we keep going until we see a pattern, and we can create the nth derivative at c times x minus c to the n over n factorial. And remember that a Taylor polynomial that is centered at 0 is called a Maclaurin polynomial. So if we construct one for, I think we did f of x equals cosine of x. If it's a Maclaurin, we know the center is c equals 0. So the value of cosine of 0 is 1. So our polynomial is going to start at 1. I know that the derivative of cosine is negative sine. If I plug in 0, I get 0. So I get 0 x to the 1 over 1. My second derivative is negative cosine of x. If I plug in 0, the value of my second derivative is negative 1. So I get minus x squared over 2 factorial. My third derivative is negative sine of x. If I plug in 0, the value of my third derivative is 0, so I would have no third term. So I get 0x cubed over 3 times 2 times 1. I'll do one more because hopefully you can see that my fourth derivative kicks back up here. So I get 1x to the 4th over 4 factorial. You can see that I don't have any odd terms. So my nth term for the Maclaurin polynomial for cosine of x is only going to have evens. So again, I know it's going to alternate. I'll check that later. But I know that all of my exponents are going to be even, and I know that my exponent is the same as my factorial. So if my exponent is only 2n, then I'm going to have 2n factorial. And again, if I want to start this, my first term has 0 x's. So if I want to start this at n equals 0, my first term is positive. This is a perfect nth term. If I plug in negative 1 to the 0, I get 1. So everything is all good. And I can see that this is an alternating series. My alternating series remainder will work here. This in fact works for all of my Taylor polynomials, which is all of my Maclaurin polynomials. And remember that with my alternating series, the remainder is less than the next term. So if I go out 5 terms, my remainder is less than the 6th term. If I go out 20 terms, my remainder is less than the 21st term. So the remainder is going to be less than f of to the n plus 1 of c over n plus 1 factorial. And this is always going to be my Taylor remainder or my Maclaurin remainder. It doesn't actually matter because we construct them the same way. So on to new stuff. So we constructed Taylor polynomials and Maclaurin polynomials. Obviously, this is going to turn into a series if we take the limit, right, as n approaches infinity, because n can't actually equal infinity. So if I have infinitely many terms, then I have an infinite sum. And that is in fact going to turn into a series, but what is now in my series is a variable. So we're going to define a new kind of series called a power series. And in fact, the definition of a power series is just this infinite sum of a bunch of terms, but now it's going to have a variable in it. So there's two ways we can write this. It's either the sum from n equals 0 to infinity of an x to the n. Notice there's no offset here. So this power series is centered at 0, meaning if x is 0, then the value of this, right, will be, so this is a initial plus a1x plus a2x squared, an x to the n. So if x is 0, all of these terms would cancel out and I would just have one term, but the center of the series is 0. I could also write a power series centered at not 0. We usually pick C for the center. I would write that as the sum from n equals 0 to infinity. I don't know if I said that right. N equals 0 to infinity of an x minus c to the n. Because this is going to turn into a initial plus a1 times x minus c to the 1 plus a2 x minus c squared plus an x minus c to the n. And again, if I plug in C, all of these terms disappear. So every power series converges at its center because all of these terms disappear. So if you remember, we created power series in class. We created a power series for e to the x. It turns into 1 plus 1x plus x squared over 2 plus x to the n over n factorial. So to turn this into a power series, this is a polynomial. It's either a Taylor polynomial centered at 0, or because the center is 0, we can call it a Maclaurin polynomial. If I want to, instead of writing out all these terms, I can write it as a sum. This is the sum from n equals 0 to infinity. I generally want to start at 0 if there are 0 x's in my first term. So if n equals 0 to infinity of x to the n over n factorial. And if you plug in 0, 1, 2, you'll see you get these terms here. And this series converges to the value of e to the x. So if I had 0.1 to the n over n factorial, the sum of this series would be e to the 0.1. If you need to rewind that and play that sentence again, that is a really, really important one. So every power series converges at its center because we construct it so that the power series is exactly the same value at the center. But what's happening around the center? So whenever I have a power series, exactly one of these is true. Scenario 1, the series only converges at its center. Meaning that if you move even a little bit away from C, the series diverges. The second scenario is that there exists some positive value that we will call R, such that the series converges whenever we are within R of the center. So we have our center plus R, our center minus R, and that R around the center creates an interval about which it can converge. So there exists some R greater than 0 such that the series converges whenever the absolute value of x minus c is less than R. And it diverges when the absolute value of x minus c is greater than r. So again, you have your center where your series always converges. If you add r or subtract r, that around that center, it will still converge. If you go past r further away, it will diverge. R is called the radius of convergence because it is around that center. And then of course we have scenario 3 where, so scenario 1 was the series only converges at its center. Scenario 2 is there's a little region around that center where that series will still converge. Scenario 3 is that the series converges for all x, also known as r is infinity. So if it converges for all x, then you can go infinitely bigger and infinitely smaller, and that series will also converge. So let's go back to this one. I'm going to get a new piece of paper.